Welcome to Math TV with Professor V. In this video, we're going to look at additional examples of how to find the volume for solids of revolution using the method of disks and washers. So the thing to keep in mind is if you're instructed to use the method of disks and washers, you're going to be taking cross sections or slices that are perpendicular to the axis of revolution. That's important. So for disks and washers, we need to be perpendicular to the axis of revolution. And what's the difference whether or not you have a disk or a washer? Well, a washer, then when you have your solid, there's going to be a hole in the middle when you take a slice. That's why you've got a washer. As opposed to a disk, it's going to be solid throughout. So the formula for the disk, the volume, is going to be the integral. I like to put the pi outside. Originally, you see the pi inside, but hey, get it out of your way. From A to B, and then you have radius squared, either dx or dy. And then if you have a washer, what's the formula look like? Well, you have an inner radius and an outer radius. Still, we can put the pi outside. A to B, outer radius squared minus inner radius squared. I'll put dx, but it could also be dy. Okay, or dy, depending on which way you're spinning. So I just wanted to work through some extra examples for you guys since my students requested just more practice, and here I am giving the people what they want. So we're going to refer to this graph here for all of the exercises that I'm going to work through in this video. Refer to the figure and find the volume generated by rotating the given region about the specified line. So we have basically three regions, 1, 2, 3. This function right here, it's not explicitly listed, but it's just the line y equals x. How do I know that? Well, look at it. It's a line segment going through 0, 0, 1, 1, so the slope is 1. Y-intercept 0. They gave me the equation of this function here. It's the fourth root of x. I can see here this is y equals 1 and this is x equals 1. And we've got this little square we're working with, okay? So I don't have any problems written down. We're just going to hop to the first one. What we're going to do is find the volume obtained by spinning region 1 about the line OA. So where is OA? It is right here. So we're going to spin region 1 about this line. I'm just going to draw a fresh picture though for each little portion. Okay, so region 1 is this triangular portion. Let's draw it out down here. Okay, region 1, and we're spinning around the x-axis. So here's 1, 1. This is OA, correct? Correct, Professor V. Okay, great. We're spinning this way. So I'm going to shade in the original region, shade it in, and I'm spinning around the x-axis. So what you need to do is reflect it on the other side. And then let's think to ourselves, if we're spinning this way, our cross sections are going to be perpendicular, or we're slicing perpendicular to the axis of revolution. So we're slicing this way. Okay, very good. So let's draw a typical slice here. And you can see it's solid all the way through, right? So I have a disc, not a washer. And since the slices are moving in the x direction, I'm going to integrate with respect to x. Now, can I identify what the radius is of this disc here? Well, I just drew a little pink segment here. That's the radius. We only have one because it's a disc. There's no hole. So you can call it uppercase or lowercase r. Nobody really cares. Now, the problems are going to get a little spicier later on. So I just want you to think of it this way when you're trying to identify the radius. Okay? The segment covers from the axis of revolution to the end of the curve, this function here. When you're trying to identify the radius, just think of it as top minus bottom. What is the boundary or the upper limit for the radius here on the top minus the bottom. And this will work well for you as you move through more complicated examples. Here we're just spinning around y equals 0, and this is y equals x. Let me remind you of all of that. This is y equals x, x-axis is y equals 0. So in this case, the radius is just going to be x minus 0, which is just x, okay? Not too exciting, but it's fine. We're gonna use this thinking for the rest of the examples, and that's also why you already studied area between curves to get used to thinking of top minus bottom, or later we'll look at right minus left. So now let's set up our integral. The volume is gonna be pi, definite integral. The limits also have to be in terms of x. Use the limits that describe the original region before you spun it, okay? So it goes from 0 to 1. And then you have the radius squared, which is going to be x squared dx. All right? And then anti-differentiating that, you have pi times 1/3 x cubed from 0 to 1. That's pi over 3 times 1 cubed minus 0 cubed. So that's just 1. So this is pi over 3. Okay, voila. Done with that one. Shall we look at another example? Okay, good. Example number 2. We're going to take region 1 and spin it around AB. Let me see, can I paste this again? Perfect, okay. So region 1, and we're gonna spin it around AB. So same triangular region, it's just this time we're gonna spin it around this line right here, AB, which is x equals 1. Again, I'm just gonna draw everything over here for myself so I can show what the solid will look like, okay? X, Y. Here's the point. This is what we're spinning around. This is AB. This is x equals 1. And again, I'm spinning region 1. Okay. Boom. So this is y equals x. And let's switch it up. Let's shade everything in purple. Okay, beautiful. We're spinning this region around x equals 1. So it's going to come over here and flip. And I mean, I don't usually draw like too much, but it's going to look something like that. Okay, cute little cone. Okay, now let's think. We're spinning around x equals 1, and we're using the method of discs and washers. So we're taking slices perpendicular to the axis of revolution. So one slice is going to look something like this. And the slices are moving up and down, right? Look at which way you're slicing. Here's a slice. I could take another one here, another one here. So the slices are moving in the y direction. That means I'm going to integrate with respect to y. So all my functions, all the limits of integration, everything needs to be in terms of y. Again, this is a disk though. There's no hole in the middle, right? So the radius, when you're trying to identify the radius, here's the tricky thing. Use the original area before you spun it, okay? So don't be looking over here. Stay right here. That's why I have you shade in the original. Don't shade the reflected one. It's just going to confuse your brain. So when you're figuring out the radius, you look at the original region, okay? Here's the radius. Okay, I have to figure out what's the bound on the right, what's the bound on the left, right minus left. Okay, so here we go. So the radius is going to be, who's bounding it over here? This is x equals 1. Okay, so on the right is 1 minus what's bounding it on the left here? Y, it's this line, y equals x. Okay, but we're integrating with respect to y, so this is x equals y. I'm going to use y here. All right. There we go. We're done. Now let's set up our integral. The volume is going to be pi. Limits of integration. Look at the original region before you spun. And we're integrating with respect to y. So give me the limits or the values of y that bound the original region. It's going to go from 0 to 1, 0 to 1, and then we have radius squared dy, like that. Okay, now let's just go ahead and FOIL it all out. So we've got pi integral 0 to 1, 1 minus 2y plus y squared dy. Most of the time these integrals are fairly straightforward, okay? Because the setup is the trickiest part. I guess they just don't want to stress you out. So antiderivative of 1 is y minus, this is going to be y squared plus 1/3 y cubed from 0 to 1. Look at the pi outside minding its business, not bothering us. 1 minus 1 plus 1/3 minus 0, right? Very good. And the ones cancel out. Again, I'm just left with pi over 3. Same answer as last time. This is getting peculiar. Okay. How was that? Let's take it to the next level. You guys are becoming increasingly proficient. I'm very proud. Okay. What are we doing now? I would like you, for problem number 3, to take region 2 this time and spin it about OA. So region 2 is this upper green region here, and we're spinning it around OA, the x-axis. All right, let's redraw everything down here. And I already start imagining like, oh, if I'm gonna reflect region 2 over the x-axis, let me draw a good amount of quadrant 4. You see what I'm saying? Yes, okay, good. So region 2 is bounded up here, here. Let's list out. This is y equals 1. This is y equals the 4th root of x, shaded in, okay, because the original region is very crucial when you're figuring out the radius, the limits of integration, everything. Then I'm spinning it around the x-axis. So it's going to reflect down here and here. It should be longer, actually. Excuse me. I hate that picture. I hate it. Okay. Good? All right. So if we're spinning around the x-axis, I'm going to take slices perpendicular to the axis of revolution, yes? Okay, this time you can see we have a washer because we have a hole in the middle. Here's the outer radius. Here's the inner radius. Ooh, let's identify them. Can I draw it better? Maybe this will auto-correct. Let's see. Ooh, yes. Outer radius. Inner radius. Oh, fabulous. Fabulous. Okay. Outer radius, inner radius, and then let's make sure the slices are moving in the x direction, so we're going to integrate with respect to x. Okay, so for outer radius, it always goes from axis of revolution to the outer edge of the solid, yeah? Okay, to figure out the outer radius, again, top minus bottom. What's bounding the outer radius on the top? The line y equals 1. What's bounding it on the bottom? Y equals 0. So outer radius is going to be 1 minus 0, which is just 1. It doesn't involve the function, the 4th root of x. That should make sense though, because even if you slice over here, yes, the outer radius is still 1. From the outside, this solid looks like a cylinder. It's only until you peek inside that you notice there's a hole, right? Like from the outside, it looks like this. You can't tell that the inside's scooped out until you look down upon it, all right? Now let's figure out the inner radius. So the inner radius is going from, again, axis of revolution to that inner edge, top minus bottom. What bounds the inner radius on the top? The 4th root of x. What bounds it on the bottom? Y equals 0. So this is 4th root of x minus 0, which is just 4th root of x. How are we doing? Good? I told you they were going to get spicier, but we're working our way there. Okay, so let's set up our integral now. Volume equals pi times, limits are in terms of x because we're integrating with respect to x. The original region lived between 0 and 1. Okay, 0 and 1. And then you have outer radius squared, so big R squared, minus little r squared, which is 4th root of x squared, and then all of this, don't forget your dx. Okay? Good. So this is pi times the integral 0 to 1. 1 minus, now 4th root of x squared, let me remind you, this is the same as x to the 1/4 squared, which would be x to the 2/4, which becomes x to the 1/2. So this is x to the 1/2 dx. Now let's anti-differentiate. So pi times, notice I'm not writing the integral sign anymore because I'm integrating already. So antiderivative of 1 is x. Over here, don't forget our rule, add 1 to the exponent, divide by the new exponent. So we'll have 2/3 x to the 3/2 evaluated from 0 to 1. So this is pi times 1 minus 2/3 times 1 minus 0. 1 minus 2/3 is 1/3, which is pi over 3. Heavens to Betsy, why are they all pi over 3? Okay, how are we doing? I have 3 more. Aren't we having great fun? Okay. Next one. Okay. It doesn't want to paste that picture back. I'll just copy this guy. Copy. Come down here. Paste. Okay, thank you so much. So for example 4, I would like for you to take region 2 and spin it about AB. So we're spinning it this time around x equals 1, region 2. Okay, I'm going to draw everything down here. Everything's going to stay in quadrant 1, right? So I'm just going to extend the x-axis a little more in the positive direction. So here's AB, x equals 1. Scoot, scoot. Okay. This is x equals 1, 1. And region 2, I'll make it green as well. That way it matches kind of. Here's region 2. And I'm spinning it around AB, which is right here. So reflect it. It's going to look something like this. Come down here. Boom. Okay, that's the other portion. It's a solid though. There's space. It's scooped out in the middle, right? So if we're spinning around x equals 1, we're going to take slices perpendicular to the axis of revolution. So my slices are moving in the y direction. That means I'm going to integrate with respect to y. And let's draw a typical, in this case, oh wow, that looks nothing like a washer. Tampoco, otra vez, excuse me. Whew. Let's get this together. Why is it so crooked though? I would like to rotate it up. There we go, there we go. I want it just a smidge smaller. Is it bothering you? There we go, wow, okay. And then inner radius. Oh no, here we go again. I know what to do. I know. Copy, paste. Let me shrink it down. Then we can just smush it right in there. Smush, smush. Squish it up like this. Oh, now it's looking better. Okay. Yay! Good. Should we shade it? Well, let's just a little bit. Yeah. Okay. You have to take your time with the graphs. Without a good graph, you can't set them up. You know what I mean? So we're going to have an outer radius and an inner radius. Here we go. And we're integrating with respect to y. So what does that mean? So this line here, that's y equals 1. This line here, this is x equals 0. Remember this function that was y equals 4th root of x? Well, instead I want to think of it as x equals y to the 4th, right? Okay, very good. And then we know this is x equals 1. So let's identify the outer radius. Allow me to zoom. Goes from axis of revolution to the outer edge of the solid. That's the outer radius. Let's figure out the bounds. It's going to be right minus left. Always right minus left. Okay. Okay. So on the right, what is bounding the region, or the radius is x equals 1. On the left, x equals 0. So this is going to be 1 minus 0, which is 1. Now let's move on to the inner radius. Inner radius goes from axis of revolution to the inside, right here, edge. Again, right minus left, right minus left. So what's bounding it on the right? X equals 1 minus what's bounding it on the left, x equals y to the 4th. How are we doing? Got it? Okay. So volume equals pi. Limits have to be in terms of y for the original region. It lives from 0 to 1. 0 to 1. Outer radius squared minus inner radius squared. Okay. Carrying on. Now it's the relaxing part, right? 0 to 1. This is 1 minus, let's multiply all this out. That's 1 minus 2y to the 4th plus y to the 8th dy, which is pi times integral 0 to 1. These ones cancel. Now I have positive 2y to the 4th minus y to the 8th dy. All right, I'm ready to antidifferentiate. Pi times, this will be 2/5 y to the 5th minus 1/9 y to the 9th. No more dy, no more integral sign. Just evaluate from 0 to 1. And then we have pi times, what's this going to be? 2/5 minus 1/9 minus 0. 2/5 minus 1/9, what's that? 18 minus 5 over 45. So pi times 18 minus 5 over 45. The little trick I do there is 2 times 9, that's 18, minus 1 times 5 is 5. And then you multiply the denominators together. Have you seen that before? It doesn't get you the LCD always, but it just gets the ball rolling on fractions. If the denominators are co-prime, then it does give you the LCD. Okay, and this ends up being 13 pi over 45. Finally, something that's not pi over 3, right? Good. Tell them thank you. Thank you for switching it up for us. Okay, that's done. 2 more. Here we go. Will it paste? No. Oh, the wrong thing. Let me go fetch the picture. Picture. Come down here. We need you again. Okay, that was example 4, I believe. Example 5. Please take region 3 and spin it about OA. Okay, so region 3, this region, spin around OA, spin around the x-axis. So I'm going to draw it separately down here. This is a nice medium level set of exercises because the graph is given. Yeah. So later we can practice some more where we have to draw everything from scratch. It's good. Region 3. Okay. Here. Here. That's region 3. And we're spinning around the x-axis. I always shade the original region because that's what you need when you're figuring out your limits and whatnot, okay? So there's region 3, and then I spin around OA. So it's gonna look something like this, right? Very good. You don't have to draw too much more, but that's like the idea. And then I'm slicing perpendicular to the axis of revolution. So slice, slice, slice. We have a washer. We have a washer. That's going to be the outside. There's the inside. Okay, let's shade in our washer. It looks so lovely. Yes, I'm not going to fuss with getting perfect shapes here, so we can just get the ball rolling. Okay, now let's decide. Spinning this way, slicing, slicing, slicing. We're slicing in the x direction, so we're going to integrate with respect to x. Okay, we have an outer radius and an inner radius. Let's identify them. Okay, outer radius from axis of revolution to the edge. Do top minus bottom. Again, I'm going to say top minus bottom. So what's bounding the region on the top, the outer radius on the top? This was y equals 4th root of x, wasn't it? Yes. And then this is y equals x. Okay, so for outer radius, top we have 4th root of x minus, this is just y equals 0, but I'll still write it out. 4th root of x minus 0, which is just 4th root of x. Okay, inner radius, let's get a different color going. Here it is, inner radius from axis of revolution to the inside of the solid. There to there. Top minus bottom, top minus bottom. This is x minus 0, so just x. Okay, you don't have to put the minus 0, but I want you thinking top minus bottom or right minus left, so it gets you in a good habit. Okay, let's set up our integral then. Volume is pi integral from, limits are for x, 0 to 1, outer radius squared minus inner radius squared dx, right? Right. Good, Professor V. Thank you, guys. Okay, so then we have pi integral 0 to 1. 4th root of x squared, we just did that a second ago. It's x to the 1/2 minus x squared dx. Add 1 to the exponent, divide by the new exponent. This is going to be 2/3 x to the 3/2 minus 1/3 x cubed from 0 to 1. So this is pi times 2/3 times 1 minus 1/3 times 1 minus 0. So 2/3 minus 1/3 is 1/3 times pi. Oh my God, we got pi over 3 again. That's just because they gave us such nice limits to make, you know, life easy. I think they took mercy on our poor souls and they said this concept is tricky enough. Let's just give them very basic integration to do. Okay, last one, the grand finale, my favorite one. Are you ready? We're going to take, oh, it still wants to paste that guy. Okay, drag with me. Come on down, come on down. We're going to take region 3 and spin it about AB. So region 3 is right here, and we're going to spin it around x equals 1. Ooh, this is exciting. Okay, let's draw everything out here. So everything's going to be in the first quadrant. I'm just going to extend the x-axis. Y. And then say this is AB. So this is x equals 1. And then region 3. So say this is 1. It's like this. Y equals x. And then this is y equals 4th root of x. I'll shade it in. This is region 3. Okay, spinning it around, x equals 1. It's gonna kind of reflect. Looks so wonky. Hold on. This portion's gonna come here. I should have had more, huh? Oh well. Yeah, that's good. We're not mad at it. Okay. We are slicing perpendicular to the axis of revolution. So slice, 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 slice. All these slices are moving up and down. That means we're going to integrate with respect to y. So everything needs to be in terms of y. Already I'm going, oh, I'm going to think of this instead as x equals y to the fourth. Okay? And then let's go ahead, draw. We have a washer. Oh. Can we use this? Wow, it was almost a perfect fit from the previous problem. Love it. Outer radius. And this one's going to be the inner radius. Oh. Okay, great. Do you want to shade it? Do we want to leave it? Let's shade it. Love it, love it, love it, love it. Okay, integrating with respect to y. Okay, outer radius, inner radius. Let's figure them out. Pause the video, see if you can figure it out. That'll be a good test. Use the original region before you spun. So don't you dare look over here when you're trying to figure out your radius. Over here only. Okay, outer radius goes from axis of revolution to the outer edge. Again, you're going to do right minus left. Who is this? X equals 1. Minus, who is this? X equals y to the fourth. Why is everything getting erased? Oh, that was the other line I was talking about. Okay. Yeah, this line here, x equals y. Okay. Anyways, right minus left, 1 minus y to the fourth. That's outer radius. Inner radius. Okay, inner radius goes from axis of revolution to that inner edge, right there. Again, we're going to do right minus left. 1 minus this line, which is y. 1 minus y. Good? Great. Limits of integration are in terms of y based on the original area before you spun from 0 to 1. Okay, so volume is pi integral 0 to 1 outer radius squared minus inner radius squared dy. Just have a little FOIL party and go. Pause the video, see if you can integrate this and not screw it up. Okay, let's double check together. Integral from 0 to 1, this is going to be 1 minus 2y to the fourth plus y to the 8th. Minus, I'm going to be dangerous and distribute the negative whilst I FOIL. Minus 1 plus 2y minus y squared. Wow, wow, wow. dy. These ones cancel out, and that's about it, right? Pi, 0 to 1. You can put it in descending powers if you want. It won't be life-changing, so I'm not going to. And there's no other like terms to combine. So it looks like in the next step, we're going to integrate. So pi times, this is negative 2/5 y to the 5th plus 1/9 y to the 9th plus y squared minus 1/3 y cubed from 0 to 1. No more integral sign, no more dy. We already integrated. Pi times negative 2/5 times 1 plus 1/9 times 1 plus 1 minus 1/3. Thankfully, if I plug in 0, everything's 0. Common denominator is what, 45? Yeah. So this is going to be negative 2 times 9, that's 18, plus 5 plus 45 minus 15, all over 45. And that's going to give me, let's see, 17 over 45. So 17 pi over 45. All right, that concludes the lesson. Do you feel more professional at finding volumes for solids of revolution via discs and washers? We can keep doing more examples, especially ones where you're just given the equation and you have to build the graph from scratch. That's really the truest way to do it. I just wanted to give you guys some more practice here. Give the video a thumbs up if you found it helpful. Leave me a comment below. Which was your favorite example? Which part was super spicy for you? Subscribe if you haven't already, and you can also catch me on Instagram, TikTok, and Patreon, Math TV with Professor V. Take care, you guys, and I'll be back soon.